Can I use this or both? Only this. Okay. Good morning. I am glad again to be back in Turkey and meet some of my wonderful friends again. What I'm going to talk about today is a project that I've been working on for a number of years. And
please continue.
Oh, okay.
I'm just fixing this.
Fixing this. Okay. And so I know that you heard from Dr. Nicholas Vassarelli yesterday. Is that correct? On continuous audit. And so I'm not going to repeat, although I'm going to talk a little bit about how my work relates to that. I'm more of a continuous reporting, and that's what I'm going to talk about today. So I'm going to talk a little bit about continuous audit, at least how I see it. Then I'm going to talk about continuous reporting. And one of the issues with continuous reporting, and this is about my work on controlling the release of sensitive information, and I'll explain what that means. And then sort of this, how we can restrict it. Okay, so if you think about, what we call about continuous audit, the question is, what can we continuously audit? And I just wanted to throw that up before I start talking about reporting. Under continuous audit, we have a couple choices. Are we auditing data? So for instance, okay, if I sell a laptop at 10 a.m., how do I audit that? Is that an auditable transaction? And if so, what can we audit about that? Okay, and that's a question that is sort of not resolved, because if you think about how we audit, okay, how do you tell that that is correct? If that is correct, then is that sufficient? Are we done? Or do I need to do something else? So if you think about, what we do when we audit, we take look at a sample, or under continuous audit, we may try and look at all the transactions. And that certainly poses a problem for auditors, because normally when you audit, you take a sample. And so if I take a sample out of, and I worked with Dr. Vassarelli on a project in Latin America. So if we take a sample of 300 million transactions, and I take 1,000, okay, that's maybe statistically significant, and that is statistically viable. But now if I end up saying, well, what if I continuous audit? Can I audit all 300 million or whatever 100 million transactions? And that becomes a problem. So if we look at a sample, then we can say something about the population, and all of your statistics courses talk about confidence intervals and so on. But the problem is, when I go to continuous audit, I have a different problem. So when I take a sample, I can say, well, I only looked at X number. And if there's some error in the population, and you take a statistically significant subset of that population, I can say with 95% or whatever confidence. But the problem starts when you say, I'm going to audit all of them. So if I go to, and there's an error, and if I looked at, whatever you want to say, looked at means all 100 million or whatever transactions, then I no longer have the option of saying, we missed that transaction. We missed the money laundering transaction. And we did a project in banks in Latin America in which we didn't end up calling them money laundering. We called them suspicious transactions. So if I am going to audit and take statistical samples, the chances of finding 6 transactions out of 100 million are very, very, very small. That's almost impossible to say that that's going to be included. But then again, if I don't, and they are guilty of money laundering, then I have a problem because I missed it. On the other hand, if I audit all of them, then you can't say that you missed it. And so now I have to have some way of saying something about that sample. So my area is sort of related to this. So instead of auditing the data, what if I'm auditing process? And we know about the processes that are going on. So for instance, how can you determine the correctness of a process? So Auditing Standard 5 looks at 2 different ways to audit internal controls or the process. The first one is design. So when we think about design, what we're saying are things like, are the steps in the process correct? And are they designed to do something correctly? And so when we look at that, correct order. So for instance, one of the things I cover in class is we may do credit checks on a sale, but if that credit check happens after the sale, after the merchandise has already left our warehouse, that's sort of a useless credit check because the sale is already, the goods have already left the warehouse. So I need to verify that. And then the other part, how do we hire internal auditors? Now, the first one is the credit check done correctly impacts a financial statement account, maybe accounts receivable and sales. So that affects that. But then if I say, for instance, okay, do I hire internal auditors correctly? So that is also a design. And in order to do that, there are a number of things that have to happen. If you look at, and I'm sure that many of you have heard of COSO, but under COSO, we have to make a statement about the control environment. And one of the things in the control environment is that you hire people that are competent, and you have competent people working at your company. So if I'm going to talk about control environment, then hiring internal auditors is an important process, that the way that I do it, okay? But now I have a problem. And that's, I also have to test what's called operationally. So AS5, Auditing Statement 5, talks about the design, are the steps there, and so on. But then I have to look at operations. And here's where we have another audit problem, a materiality problem. Suppose they say, we look at all credit checks, and we find, and in my class, I had the students doing 100% audit of, I have a 300, well, no, I have 1.5 million transactions that they have to look at and do some analysis using some techniques that we talk about in class. But so that, let's say that all credit checks done before shipment. Well, here's the problem. What if not all of them? Or what if not all internal auditors are hired correctly according to the guidelines that are set in the design? So what do you do? And this is where, when we talk about artificial intelligence entering the audit sphere, that becomes a problem, because I can say, not all of them were, or not all the shipments were done with that. But now, how do you evaluate that? And AI systems are not, I won't say not capable. They can make judgments, but how valid are the judgments? So for instance, okay, let's say that 90% of all credit checks happen before the shipment. Is that okay? Are the processes working correctly? Well, what about the 10%? And now I have to go through and make a materiality judgment. Now that has a materiality judgment again on accounts, in a particular account, sales, accounts receivable, inventory, and so on. If those aren't all done, that process is not done correctly. On the other hand, what if not all internal auditors? We have 90 internal auditors and 10 of them are not hired correctly. Exactly what do we do? And that's where judgment comes in. Is that a problem? Is that okay? And so when we talk about AI in auditing, that becomes a question, is whether or not it can do that. Well, it can do it. Certainly I can tell it to do it, to any program to do that. But the question is, what comes out? Are we going to rely on it? Are you as an auditor willing to go to jail if it finds out that, they weren't, and something happened, and, some person lost their life savings or whatever? Are you willing to stake your career, your reputation, and maybe your freedom on that AI system to make that judgment? Okay. So this is a paper by someone that I'm going to, that I'm working with, that we're going to talk a little bit. I'm going to talk about another paper that we're doing this afternoon. Normally Raditz, who is going to be here, but things happen. So I'm going to present that second paper. But we have a paper that is being revised now on software quality and how to look at the design of process. So look at design of software and use it to make statements about the quality of the data that's going through the process. And so that paper will be coming out, revision should be coming out another month. But what I want to talk about is continuous reporting. Now, continuous reporting has these characteristics. And there's a paper, that bottom paper on query issues, that is now getting a little bit old, but speaks a good deal about some of the topics that I'm going to bring up right now. Under continuous reporting, we have this notion that it's zero time lag. And what that means is, as a transaction is happening, I can get it. That is, if I want to know how many shirts Migros has on hand in one of the stores, they know that as soon as it's sold, their inventory is depleted, and they have that information. So should I be able to get that? Can I get zero time lag information? The other part of it is, and this is another point that I bring up in that paper, is how are we going to allow continuous reporting? Do I allow continuous reporting where they get to do free form? And what I mean by that is, you go to Google or something and type in anything you want, what were sales yesterday in a store in Izmir or whatever. Can I do that? And that's a different question than if I can say, show me the income statement or show me the cash flow statement. So we have a number of predetermined formats that if we use only those formats, then we have sort of restricted the users to what we think is important. And when we talk about continuous reporting, one of the real issues is, can I really supply users with information that is relevant to them? And maybe information that other people have, for instance, management. And if that's the case, then I have to go to non-predetermined format. I have to allow sort of this free form. And that's another problem that I bring up in that paper. But one of the biggest problems is if I allow people to write their own queries, we have two materiality issues. One is, how can I prove that the data that you got matches the query? And then the other question is, did I really understand the query? Now, I worked with a doctoral student who's now at Google. And one of the things that we went through with his dissertation was that I can show, so if I write a query in Google and I say, show me all the websites that have gold and investments in them. And we can prove that everything that comes out from that query matches that statement. That is, every document that comes up has that in it. The question is, and this is something that is still not provable, and I'm thinking about ways to prove this, is you didn't miss one. So are there, if there's, and he was working on a document collection of a terabyte. So I can prove that everything that came out matched the query, but I cannot prove yet that everything, that he didn't miss one, that the software did not miss one of the important documents in that collection. And so when we start looking at how we're going to use it, it's okay if, my students use Google to find places to buy accounting textbooks, and one of the sites doesn't come up. That may not be, well, it's a problem for them, but not necessarily a huge problem. But on the other hand, if I say we are going to represent or give you access to corporate information, and I can't prove that we gave you a really valid subset of that, or valid set, or whatever you want to call it, then we have a problem, because now we think we're getting something that we're not really getting. Okay, but that's another question, and in that paper I go over that. But here's what I want to talk about today, and it's the notion of controlling inferences. So under continuous reporting, if I can ask enough queries, that is, if I can ask, what was this, what was this, what was this, if I give that free form, then at the end I can make an inference about something that I may not have been allowed to do. So here's an example. So if on Monday I make a query about raw materials and finished goods, how much titanium do you have, and how many of this do you have? And I ask that on Monday, and then again on Friday I make that same query, and I say, and I also about sales. Now I may have been able to back into to figure out what your production process is for that particular good, because I know how much titanium goes into it, or I can look at the entire set of ingredients, and I can also have an idea about how long it takes you to do it if I can ask that query. So I can, if I allow continuous reporting and I allow sort of that non-predetermined format where you can ask anything you want, then all of a sudden I've opened up the system to possibly revealing things about the company that you didn't want to know, or you said you wouldn't know, should not be allowed to know. So I want to just talk about representation issues, because this sort of comes into this problem as well. Okay. So an inference is a conclusion about some data. So if I obtain data about raw materials, okay, how much is in there, then I can make an inference. And so production has to make this inference. Do we have enough raw materials to make, 1,000 units this week or whatever? So that's an inference after making a query. So I query how much raw materials I have, and I make an inference about or whether or not I can do something. Okay. So now, so here is a problem that I have to briefly touch on, because what we do in this next set of slides is talk about representation. And representation is a problem for any sort of query system, for any sort of system that wants to get data, is how do we represent the data? And so I'm looking at some of our work, and we just had a monograph published by the American Accounting Association on ontologies. And I don't want to go into a long discourse on ontologies, but basically what an ontology is a representation of a particular domain, and it looks at both the objects that are in the domain and how they're related. What are the relationships between them? And so when you talk about an ontology, what you're really talking about is taking a slice of reality and representing it somehow. And it turns out that that has a significant impact on how the system functions in terms of queries and reporting, because we talk about things every day. So if a computer system wants to understand what you're asking, it has to have the same representation. Otherwise, we will have this mismatch and you won't get what you think you're getting. So for instance, down here, okay, here's that purchase transaction where raw materials include purchases from a vendor. So this is a representation of that, of a transaction that we call a purchase. It looks at things that are in the domain and how they're related. So here's the problem, okay, what I'm going to address right now. When we talk about ontologies, we're looking at sort of this, what we call this semantic interoperability spectrum and this continuum. And Leo Orbst, who is a computer scientist from MITRE Corporation, originally published this. We've adapted a little bit in that monograph that I talked about. But these two papers that I mentioned on here, these are fairly old, but what we look at is where in the continuum we're talking about representing and how we're using it. And I don't want to go into what the issues are if you try and represent data at different levels in the continuum, but it turns out that interoperability becomes a problem. Okay, and I'll just leave it at that. And if you have some questions about that, I can go into that in a little more depth. But these two papers that I put down here look at what's called at the lower end of the spectrum. I'm going to talk about what this is at the upper end in logic. Okay, so here is, and I don't want to, again, I have another paper. It's on metaphysics of internal controls. I'm trying to remember, a couple of people maybe from Turkey have downloaded this paper, but basically what that talks about is how we represent information systems. And when we talk about an ontology, if I can represent it using these axioms, okay, then I can do certain things, in particular what I'm about to do. And I cover in more depth in that metaphysics of internal controls. The one that I'm really interested in right now is this alters, okay? And what that means is the alters axiom says that we have certain events that happen that alter attributes. And there are 4 ways to alter an attribute. I'm going to concentrate on one of them. One is to update it, one is to insert it, one is to delete it. But the one I'm going to concentrate on for the next part of the talk is on the view. That is, when someone looks at something, the attribute has changed. It is now, in a sense, available. That information is now available to that person, and it wasn't available before. So we do have a change in there. Okay. So again, we are looking at a very specific axiom, and I'm looking at a portion of that, the view axiom. So what it says is inferences focus on viewing. So if someone has looked at something, they can make inferences. So if someone looks at the quantity of titanium in there, they can make an inference about whether or not I have enough production this week. So by looking at something, I'm allowed to do inferences. So the other three, the delete, insert, and update, are not relevant for what I'm going to talk about right now. So what we want to do in controlling sensitive information is control viewing. What have people looked at, and how do I stop them from asking or seeing something that would allow them to make an inference that they shouldn't be able to have? Okay, so I'm going to look at this numbering, and this is an interesting, when you are working on some of these issues that I've been addressing, I get to read theory of mathematics. Okay, I get to read, I just finished a little sub-course on quantum physics, and those are the things that you get to do when you both have tenure and are working in this area. So I'm not going to say I have any sort of expertise in quantum physics, but it turns out some of the things that I'm doing relate to some of the issues in quantum physics. So anyway, so what Kurt Gödel did, so if you think about, and I'm going to give you a brief discourse on the history of mathematics. In the early part of the 1900s, we have various mathematicians who have, there are certain kinds of theorems that they're trying to prove. And one of them, for instance, is the theorem about, that there's multiple ways to represent, or you could, the Pythagorean theorem, a squared plus b squared equals c squared, also holds at higher levels of powers. And that's another theorem that they're trying to prove. So at the beginning of the 1900s, we have a number of mathematicians that are looking at those kinds of theorems and trying to group them into sets of theorems, okay? And one of the reasons for doing it, the real reason for doing that, is if they can do, and these are, remember, these proofs are being done without computers. If I can show that this set of theorems can all be proved using the same techniques, and this one can be all proved, and so on, I'm now sort of ahead, because now I can say, the techniques I used on this theorem will be usable on this theorem as well, and we'll be able to prove that and either true or false. And so they, Bertrand and Russell, okay, which I reference here, this by Principia Mathematica, which is a 3-volume set, which I'm sure you've all read in your introductory accounting classes, of all the axioms in mathematics, and how to, and the goal for Russell and Whitehead was to get all the theorems, or excuse me, all the axioms from mathematics. And so now we have everything we know about mathematics, and then we can use them to prove things. And so we're far ahead, okay, now after the Principia Mathematica. But then along comes Kurt Gödel, and he shows in a proof, which was in German, and I don't know German, so I had to wait for the translation. But it's a 100-page proof that you cannot end up with that in all systems that are done with axioms. And what that means is that, and what he came up with is that you can come up with, and I have some examples, okay? So for instance, this sentence is false. Well, that's neither true nor false, because if it's true, then it's false, but if it's false, then it's true. And so you end up with these unprovable things. And what Gödel proved was that in any system that's developed using axioms, you are going to end up, you have the possibility of ending up with unprovable statements. And so you think you're going to be able to prove this theorem, and you go through and go through, but you can not realize until very, very late in your process, and maybe not at all if you haven't gotten there yet, that it's unprovable, that you can never arrive at a proof. It will be unprovable. And so basically what he did was the proof, and I'm going to just go briefly through part of the proof. And what he did was use prime numbers to represent all those axioms. And what he did was, with those axioms, he was able to, using their integers. So we use prime numbers, and you know about prime numbers. And so basically he numbered all the axioms and showed that if I number the axioms, I can, and his proof, as I say, it's about 100 pages. So I'm still redoing pages 1 through 70, okay? If you want to look at it, I encourage you, but I'm sure that it will make your mind numb after about another 10 minutes, okay? It's very, but anyway, so what he did, just briefly, is he numbered all the parts of axioms. So here's one of the axioms that I have in that earlier part, and this is one that I use in the metaphysics paper, but I can number all these things with integers. Now, what does that give me? Well, so if each axiom, and when I use prime numbers, one of the things that's nice about prime numbers, that it gives me a unique representation of all the axioms. So every axiom becomes a unique integer. So every axiom is a separate but unique integer. Okay. Now, once I have those integers, okay, so then I can say what it needs to take an inference. So K, that inference, okay, to know something requires axioms, X1, so on. And so that product becomes the integer value of the data that you need to make a particular inference. So that K is a set of axioms that can be represented as an integer. And so now I have an integer which says to make these inferences, I have a K. And so every inference from K is now as an integer value. So I have an integer, and integers are really nice because they do things like when you multiply them, you get another integer. And if I do certain kinds of division, if I don't end up with an integer, which is what I'm going to do right now. So first of all, so KI knowledge, that whatever I can make from that inference. So now I can define sensitive information as the product of certain kinds of axioms. So if I know this, and this, then I can make an inference about something that's sensitive. And so now my sensitive, K sensitive, it allows me to, if that set of KI includes K sensitive, that is, if the integer value of everything that I know includes that K sensitive, then I can make an inference about something that I shouldn't be able to make an inference about. Okay. So again, I go through that, if P is the product of all queries P person has made, includes K sensitive, then they know that they know sensitive information, that they can find that out. So how do I prove that? Well, here's a test. Okay. So if the product of all the queries, if I divide by K sensitive, remember these are integers. If I divide and I get a whole number, because an integer divided by another integer, if I don't get a whole number, that means it doesn't include it. If I do, then it does include it. And then it can now test to see whether they do that. So again, this is a little bit, in the paper, I go through a little bit more detail, but basically that allows me to do this. It says that, okay, I've already responded to this, and you have this integer of everything that you know. If what you're about to ask allows you to make that includes the set of things that included, say, K sensitive. So in other words, if I ask, how much raw material did you have on Friday? And if I know that set now would include what I would find out includes that, then the system can stop responding and not answer it. And, you do that as well. So whenever I give this talk to non-computer scientists, and I guess auditors too, right? But anyway, if you think about, if you went to, and I use this for my students, if I go to a bar and someone sits down next to you that you don't know and starts asking you questions, and, are you a student? Yeah, I'm a student, and okay, students have it great. They get to go on, oh yes, I get to go away on spring break. Are you going somewhere? Yes, I'm going away. And then, 5 minutes later, that same person asks, don't all students live in the same? Yeah, I live in, wait a minute. Now, if I tell them that I'm going away and where I live, then that combination of information allows that person to know that my apartment will be unguarded for that week. Okay. Now, it's not either one of those pieces. It's the combination. It's the A times B, that integer of what they know. So a person would know oh, wait a minute, I can't tell them that. And it's not saying either one of those, it's the combination of those, that product of those two. And so that's when I want to stop talking to the system. So if I do this, then I can have a system that stops answering questions, that doesn't do continuous reporting to the point where it would reveal sensitive information. And that becomes critical when we start thinking about our AI systems going to keep talking to you forever. Will you be able to talk to them and ask questions? Okay, forever. Now, this is another issue that's related to this is what we call collusion. And if two people talk to the same system and get one person gets where you live and the other system gets where you're going to be away, then we have to look for collusion where those two people talk to each other. Now, we do that right now. When we look for terrorist threats, when we look at terrorist threats, what we actually look for, one of the things that we look for is query trafficking between two nodes on the internet that we know are colluding, are talking to each other. So if this person asks this person asks this, we know that outside the system, they're going to collude and they'll know something that they shouldn't. So we do look for traffic. That's one of the ways that we look for threat enhancements, is when we have traffic between two nodes, okay? So anyway, so I can do this now, and I can prove that, okay? Okay, so continuous audit, define what is audited, and that's something that I think is a question for all of us is, if we go to continuous audit, exactly what are we going to be able to audit? We audit data, and in my software paper, I'm looking more at auditing process. I want to know how the process is working, and we have in that paper, we look at ways of evaluating software which is generating the process and how I can get a value of what's going on. Okay, but continuous reporting isn't ideal. It is this thing that I think, if you look at various financial bodies, the SEC and in the United States, that we would like users to be able to ask questions and find out on their own. Financial statements, to my view, okay, and also Dr. Vassarelli, are fairly useless because they come out a year and a quarter. Like we're getting, financial statements that come out in April for some things that have happened last year. We know that more current data is always better if you can give it to them. But now the question is, how are you going to do it? Are you going to be able to audit the data, or do you audit the process? And my view, and again, this is my view, but shared by a number of regulatory bodies, is that continuous reporting is an answer. But now if we go to continuous reporting, we have to define what it means to continuously report, okay? Can I hold back information, or do I have to give it as soon as it hits my books, my computer system? Do I have to make it available to you? Can I hold it back? And now, if I can't hold it back, then we have that problem with sensitive. So how can we allow continuous reporting, but restrict sensitive information? That's what I was just talking about, okay? So we create axioms again with first order logic as a representational tool. And then we have to also prove that that representation is complete. And so what I've done in the metaphysics paper is go through a number of proofs of I can derive things like I can derive all the financial statements using my axioms. I can also derive organizational structure, who reports to who. Do we have segregation of duties, for instance? Okay, I can derive all that. But it's interesting, as I say, the Gödel numbering allows us to make inferences and represent them as integers so that I have a control over what is released and know when information has been released. And that's it. Thank you. Question? Have all of you read Gödel's proof? That's the test for later today, right?
Thank you very much, Professor, for your very inspiring speech. We appreciate it.